Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will be learning about angles of a triangle. And in order to learn that, let's first look at the following problem. In the diagram below, segment AB is parallel to segment DE. Measure of angle ABC is equal to 41 and measure of angle CDE is equal to 38. Compute the measure of angle BCD. So how would you solve this problem? It seems like that here we're dealing with parallel lines, and maybe we can use one of the theorems that we developed in the previous lessons. But the transversal is not just one segment. Now here we have segment BC and segment CD. So how do we solve these types of problems? The best way to do this is draw an additional line that is parallel to segment AB and segment DE respectively, going through point C. Now, according to this image or diagram, we can now refer to alternate interior angles. For example, this angle and this angle are alternate interior angles, and also we have this angle and this angle here that I'm drawing also to be alternate interior angles. So if angle ABC is 41 degrees, then what is angle BC? Well, let's call that point F here. So what's the angle or the measure of angle BCF? Well, it turns out that that is also 41 degrees, because if two parallel lines are cut by transversal, in this case transversal BC, then the alternate interior angles are equal in measure. Similarly, we have angle CDE, which is 38. So therefore, angle FCD is also 38 degrees. And again, because if two parallel lines are cut by transversal, which is transversal CD in this case, then alternate interior angles are congruent. And notice again that this is a parallel line. It's parallel to segment AB and ED respectively. So this means that the measure of angle BCD is just the sum of 41 and 38. So therefore, the measure of angle BCD is just 79. Again, we were able to solve this problem because we used a theorem, which is if two parallel lines are cut by transversal, then alternate interior angles are congruent or equal in measure. Why were we able to add them up? Well, we were able to add them up because the whole is equal to the sum of its parts, which is also known as the partition postulate. As you notice so far, there are many definitions, postulates, and theorems that we can use in geometry to solve problems either of algebraic nature or in terms of proofs. As you may have noted from my previous lessons, there are many postulates and theorems and definition in the axiomatic system of geometry. If you look closely, for example, we have tons of definitions here. We have many postulates and properties that we have developed, many theorems, and there will be more theorems to learn in the next coming videos, and also specific conventions in geometry. Well, the question is, where do all these postulates, theorems, and definitions come from? Well, it turns out that Euclid of Alexandria is considered the father of geometry. He's actually the one who formulated all these postulates and theorems and definition and the conventional system of geometry. And that's why sometimes I refer to this type of geometry the Euclidean geometry. Furthermore, Euclid developed famous books called the Elements. So he developed 13 books where it's just full of definitions and postulates and propositions and mathematical proofs of these propositions as well. And the main 5 postulates that Euclid developed are as follows. A straight line segment can be drawn joining any 2 points. Basically, if you have 2 points, you can draw a line through it. Or any straight line segment can be extended indefinitely in any straight line. Or given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as a center. All right angles are congruent. If two lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than two right angles, then the two lines inevitably must intersect each other on that side if extended far enough. This postulate is equivalent to what is known as the parallel postulate. Euclid also developed common notions, such as things which equal the same thing also equal to one another, which is the transitive property. Or if equals are added to equals, then the wholes are equal, which is the addition postulate. Or if equals are subtracted from equals, then the remainders are equal, which is the subtraction postulate. Things which coincide with one another equal one another. The whole is greater than the part. Again, these are all the common notions that are also known as postulate, right? We accept these notions to be intrinsically true. So one of the famous theorems that Euclid developed is about triangles. And the theorem states that in a triangle, the sum of the measures of the three interior angles is 180. So when he first developed the theorem, he needed to prove this to all people that this is always true. Now, how do you prove this? How do you prove that the sum of the measures of all three interior angles is 180? Well, let's set up the proof here. Let's say you're given triangle ABC. We want to prove that measure of angle A plus measure of angle B plus measure of angle C is equal to 180. Again, what we want to do here is make use of any parallel line theorems that we have developed so far. Okay, so here's the given and what we want to prove, and we're given triangle ABC. How can we prove this? Well, we need to somehow draw a line to this, right? We need to construct a line such that it's parallel to segment AC and then use the alternate interior angle theorems or the parallel line theorems. So let's say here we are drawing a line such that it's parallel to segment AC as shown in the diagram. Let's also label some points on the line so we can refer to it. So let's place points D and E as shown. So what will be the reason here that we can construct a line parallel to segment AC? Well, the reason is that let's assume that there's a line somewhere like this, okay? And let's assume there's a point that is not on the line. The question is, how many lines can we draw through this point B such that it's parallel to this line? And the answer is only one, okay? So, and that is one of Euclid's postulate that we can use here. So the postulate states that given a line and a point not on that line, there is one and only one line parallel through that point that is parallel to the given line. And that's the reason why we're able to construct line DBE parallel to segment AC. So what do we notice here? Well, we actually know that this angle here plus this angle and plus this angle here, which is angle DBA, angle ABC, and angle CBE, they all add up to this big angle here. And we know that that is because of the partition postulate. Now, what else must be true about angle DBE? That it's 180 because it is a straight angle. So what we can do now is simply substitute step 3 into step 2 to say that the measure of angle DBA plus measure of angle ABC plus measure of angle CBE is equal to 180. Now, if we look at the measure of angle DBA, this one, right? Can we say that this angle is equal to another angle in the diagram? Yes, we can. This angle is the same in measure to this angle because here we have two parallel lines cut by transversal AB. So let's write this in the statement reason table. And the reason for that is that if two parallel lines are cut by transversal, then alternate interior angles are equal in measure. We can similarly state that the measure of angle CBE, this one, has to be equal in measure of angle C. because of the same exact reason as stated before. So now we are stating that the measure of angle dBA, that is equal to measure of angle A. But the measure of angle dBA is also here, right? So we can actually replace that with measure of angle A. And in a similar manner, we know that the measure of angle CBE is equal to the measure of angle C. So that means that this angle can be replaced with measure of angle C. So let's write that in step 7. So here we have now measure of angle A plus measure of angle ABC plus the measure of angle C is equal to 180 because of the substitution postulate. Now, as you noticed, here we're using the measure of angle ABC instead of measure of angle B. Why is that? Well, the reason is because if we look at the diagram and we say measure of angle B, then we don't know if we're referring to this one or to this one or to this one or to the whole measure of angle B, right? So therefore, I'm writing measure of angle ABC. But in reality, measure of angle ABC is the same as measure of angle B without the line on top. Therefore, we can simply state that the measure of angle A plus measure of angle B plus the measure of angle C is equal to 180. And thus, we have proven this theorem that it's always valid. Now that we have proven the triangle theorem, that the sum of all the interior angles add up to 180, we can solve problems of this sort here. For example, here we know that in the diagram, line M is parallel to line N, segment AB is perpendicular to line M, angle ADC is equal to angle BCE, which is equal to 3x, okay? So here we're referring to the measures, obviously. And we also know that the measure of angle CEB is 50 degrees. And the measure of angle BCD is equal to x. What is the value of x here? Well, since we know that segment AB is perpendicular to line M, and then we know that line M is parallel to line N, then what can we say about the angle here at B? We can say that this is also a right angle here. And there's a theorem to this, right? That says that if one of two parallel lines is perpendicular to a third line that is intersecting those two parallel lines, then the other line needs to be perpendicular as well. So that means that here we have 50 degrees, right? And we have 90 degrees here. That means that this angle has to be 40 degrees, okay? Again, why do we know this? Because we use the triangle theorem that we just developed. So what can we say about this angle here? So I'll use a different color here. What can we say about this angle? Well, we can express this angle also in terms of x, right? We know that in triangle ACD, everything sums to 180, right? So we know that 40 degrees plus 3x plus, call it measure of angle ACD, everything sums to 180 because of the triangle theorem that we developed. So that means that the measure of angle ACD has to be equal to, if we apply the subtraction postulate, 140 degrees minus 3x, okay? So now we know that this here must be true for this particular angle. So how do we solve this problem now? Well, we know that this here is also a straight angle, correct? That means that here we can say that 140 minus 3x, and then we have plus x and then plus 3x, right? That has to be equal to 180. It turns out that the 3x cancel here, and we're left with x, or 140 plus x is equal to 180. So we can now subtract on both sides, and we end up with a value of 40 for the value of x, okay? So again, this was just an example on how we can use the triangle theorem to solve problems like this. Okay, so that's basically it for today's lesson. Again, thank you for watching and have a wonderful day.